And then that allows me to write it like this. The top I can write as negative 4 to the n minus 1 times negative 4 to what power? Negative 1, right? We're splitting this up, keeping the n minus 1 on it, and then the negative 1 on it is two different factors. And on the bottom, I'm going to do something similar. I'm going to do 7 to the n minus 1 times 7 to the what? Second power. Because, right, the n minus 1 is going to go here, and then these two powers, 1 plus 1 is 2. So I'll put those here, 7 squared. Y'all see how I'm doing this? I'm massaging it into what I want it to be. Yes?
So you plus 1 on there is just for our benefit. Otherwise,
The
we can only do plus 2 instead.
You could just do plus 2. Yeah, of course, yeah. I was trying to get you to see that I'm basically inserting a hidden 0 here, right? Minus 1 plus 1. All right, now that's good because notice that the negative 4 is to the n minus 1 and the 7 is to the n minus 1. Since they're both to the n minus 1, I can create a fraction out of those and raise the whole fraction to the n minus 1. And then also on the other one, the negative 4 to the negative 1, I can drop the negative 4 to the bottom, can't I? And make it a positive one. So here's what I've got. I've got sum n equals 1 to infinity. Let me do this first. I'm going to go negative 4 over 7 to the n minus 1. That is this, right? That's that. And then this comes downstairs as a negative 4, joins the 7 squared that's down there. And then this up front here is just some number, right? It's A. That's A, isn't it? That's our A. The reason I know this is A is because n has no impact on this, right? N is only impacting that exponent right there. So this is my A and that's my R. So what is A? I need the number though. What is A? Negative 1 over 196? Yeah? I just put the negative, we just put the negative on top or out front, right? So you're doing 49 times 4. And then over here, we have R is equal to negative 4 over 7, right? Negative 4 over 7. And now I look at the absolute value of that. Absolute value of R is the absolute value of negative 4 over 7, which is 4 over 7, which is less than 1, right? So I have convergence. Yes?
For A, you could have just rewritten it as the negative 196, right? Instead of just leaving it like that in the step above.
Oh, yeah, yeah. I put it here what it is. But yeah, I definitely probably, well.
So as long as it goes less than 1, it always converges?
As long as R, the absolute value of R is less than 1, then it converges. Which I'm not proving, and I feel terrible, but yeah.
What happened to the 7 squared?
Right here? So that becomes 49, and then we multiply by negative 4, and that gives us the 196.
And then that part, yeah.
These two, so if you have x, let's say you have x squared over y squared, you can turn this into x over y squared, right? Because the squared could apply to the top and bottom and become this. I'm doing the reverse. I'm going from here to here. So since they're both to the n minus 1, I just put them together into a fraction and then to the n minus 1. Yep. Okay, so it converges, yes? What does it converge to? So it converges to a over 1 minus r, right? A over 1 minus r, which for us would be a, which is nasty, 1 over 196 over 1 minus, careful here, 1 minus r. What was r? Negative 4 over 7, right? That double negative is important because it's become an addition. You don't put the absolute value of r here. You put r itself. And now this is going to be, I'm going to do it over here. This is negative 1 over 196 over, what's the bottom? 11 sevenths, which is flip, right? Yeah, negative 7 over, what is that?
It comes out to be 1/308.
Reduced?
Yeah, reduced.
What is that? That's 1960, 1971? Someone check. 1971, is that what's on the bottom? Before it's reduced.
I think it's
It'd be like 2000.
yeah, it should be 1960 plus 196.
2000.
Oh, plus 196. What am I doing? What did I do? Wow. All right, what is it? What's the bottom?
156. It's 2,156.
2156. Okay, here we go. Arithmetic, just ugh. What?
So if the
What? I'm sorry. Yes, sir. What?
If the absolute value of r equals 1, it diverges?
If the absolute value of r equals 1, we have divergence. Yep, exactly. Because think about what would happen. If the absolute value of r is equal to 1, then this is either a 1 or a negative 1. Let's say it's 1. If it's 1, then you just have a plus a plus a plus a forever. That's going to diverge. All right, moving on. Now, for this example, I don't give you the formula. I actually give you the series written out as a sum. And you have to come up with a formula, and then you have to show it's geometric. Then you have to determine if it converges or diverges. So this is the type of problem that I really expect you can do. That all was just to make sure we got the mechanics of it down.
When it says to find the sum, that's just saying what it converges to.
Yes. Yep. The sum is what it converges to. So I've been doing Cal 2 for a long time, and every time I give the final exam, I'll tell my students, look, if I tell you to find the sum of a series, I'm already giving you a huge hint. I'm telling you it's geometric or telescopic, because I just told you there's only 2 series that we can find the sum of, geometric and telescopic. So if I say find the sum of the series, it's one of those 2. You know that. I'm giving that to you. And students will still forget, oh, wait a minute, that's a hint. They'll just forget about it. So I state to you again, as I do every semester, if I ask you to find the sum of a series, you know it's either geometric or telescopic. And the sum is what it converges to. All right, so I need to come up with a formula. So I need to somehow wrap my head around what's going on here. I'm seeing that it alternates, right? So this is basically what your test is about on Thursday a little bit, right? You have to come up with a formula that generates the sequence of this series, right? So let's try and come up with the formula for like the a sub n. So I need to alternate, so I'm going to use -1 to what power? I need to start, I can do either n plus 1 or n minus 1. It's up to you. What do you want? You want -1? I could use +1, but n minus 1's better because that's what geometric has in it, right? N minus 1. Now, if I did n plus 1, and then I had to go get it to geometric, I'd have to do a hidden 0 in there, -1 plus 1. All right, that should create the alternating, right? Starting with positive. Right? If I plug 1 into this, I get 0 up here, and then -1 to the 0 is 1, so that'll give me a positive. And then when I plug in 2, it'll give me 1 up here, and that'll give me a -1. So it should be positive, negative, positive, negative, positive, negative. That part's done. Now I'm noticing that the numerator are all powers of 3. 3, 9, 27, 81, but the very first one is 3 to what power? Yeah, so 1 in the very front on top of the 4 is 3 to the 0, right? So that means I need 3 to what power up here to start at 0? N minus 1. Remember, n's going to start at 1. So when I plug in 1 into this, I need this to be 0, so I get 3 to the 0, which is the 1 up there. And then when I plug in 2, I'll get 3 to the first, and yeah? What about the bottom? 4 to, those are all powers of 4, right? But I want to start with 4 to the first power here, right? So it's going to be 4 to the n, not n minus 1, right? Because You need to be 4 to the first when you plug in 1. So there it is. I think that should do it, right? That's the formula for this sequence, and now I need to add them up. So now the series we're looking at is sum n equals 1 to infinity of, let's see, -1 to the n minus 1 times 3 to the n minus 1 over 4 to the n, right? But I'm going to write what? N minus 1 plus 1 because I know where I'm going with this, right? I'm going to go, I'm trying to get it to geometric. It was just n, but I'm making it minus 1 plus 1.
Oh, you're doing that to factor out like the power.
Yeah, that's so I can rewrite this as 4 to the n minus 1 times 4, right? Trying to get everything to n minus 1 so I can go to the geometric formula. Did you send me a text? Okay.
But don't worry.
This morning, right? Or something? I don't like to click links on texts until I verify that the person meant to send it. All right, -1 to the n minus 1 times 3 to the n minus 1 over 4 to the n minus 1 times 4, right? That's what this is. And now I have a bunch of stuff with n minus 1 powers, right? All 3 of these factors, all are to the same power n minus 1. So I can put them all together. I can do what?
That's R.
That'll be R. We'll put it all together first, though. Are there any questions on this? So now I have this. I have sum n equals 1 to infinity. Okay, I have a 1/4. Then I have -3/4 to the n minus 1. So when I put -1 times 3 divided by 4, right? That's -3 over 4. And then this 4 on the bottom, I just shove it out front as a 1/4.
Why is it a 1/4?
Because it's on the bottom, right? So it comes out in the front and it needs to be written as a fraction. So that's it. That's geometric, right? A equals 1/4. R is -3/4. I'm not going to write it this time, but do we all agree the absolute value of R is less than 1?
Yes.
So this converges. This converges to A over 1 minus R, which is 1/4 over 1 minus double negative, -3/4. So this is 1/4 over 7/4. And then when you flip, you get 1/7. What's your question, sir? What's your question? Yeah.
When you're combining the numerator, since those are being multiplied, wouldn't the powers also get added together?
Well, we're using a different property. We're using this property. If I have x to the n, right, times y to the n, I'm writing that as x times y to the n. Not this. I'm not doing x to the m times x to the n is x to the m plus n. What you're saying is, do we add these powers? Only if these are the same bases, right? These two things have to be the same. That's when we add the powers, right? X to a power times x to a power, we add the powers. But if you have different bases, same exponents, we just put them together in parentheses with the power on both of them.
Okay.
Yeah. Good? All right, let's see what the next thing is. Pardon?
Real though?
Yeah.
Really? All right.
This problem seems like it's out of place, right? Like all of a sudden, like where did this come from, right? So it turns out that in our number system, any number that either like when you write it out in decimal form, that either terminates or repeats has a pattern. Like any number that either terminates or repeats can be written as a fraction. Okay, so every number that repeats or terminates is a rational number. Okay, it's an integer divided by an integer. There are numbers where they go forever and it doesn't repeat, there's no pattern, right? Those are called irrational numbers like pi, square root of 2, e. Okay, so every rational number either has a pattern of repeating or it stops. Yes?
Terminate means that it has like 0 repeating?
Yeah, like 0 repeating. So it would be like if you take 1/4, 1 divided by 4 is 0.25, terminates. You could say 0, 0, 0, 0, 0, but then that's repeating, right? That's the same pattern of 0, 0, 0.
Is pi a rational number then, or repeating?
Is pi irrational or rational? What did you say?
Like, does it eventually repeat?
No. No, pi does not have a pattern to it, so it's irrational. So what I'm telling you here is to rewrite this repeating decimal as a fraction. I mean, that repeats, so it's a fraction. What is the fraction? So the way we do this is kind of weird, all right? Let me write some stuff out. Do you all agree that that is the same as 2 plus 1/10 plus 3 100ths plus 4 1,000ths plus 3 10,000ths plus 4 100,000ths. When I say this, you have to know coming into this class that the first digit behind the decimal is the tenths position. That's the hundredths position, thousands, 10,000s, so on and so forth, right? So do you all agree that that's what we have?
Yeah.
Yes? Now, I have repeating, right? It repeats with the 3, 4, 3, 4, 3, 4, 3, 4. So what I'm going to do is I'm going to group the 3 4s together. This right here could be rewritten as 34 over 1,000. Now, if you don't believe that, just multiply the top and bottom of this by 10. And you get 30 over 1,000, wouldn't you? And then you add them together and you get 34 over 1,000. Right? And I do the same thing here. This would be 34 over what? 100,000. Right? Because you would just multiply the top and bottom of this by 10. Then they would have the same denominator. And then you add across the top, you get 34 again on top, and then over the 100,000. Okay, plus. Any conjectures on what the next one is? 34 over...
Add 2 zeros.
Add 2 zeros, yeah. Just add 2 more zeros. So 7 zeros? Right, this had 3 zeros. That one had 5 zeros. This one has 7 zeros. The next one would be 34 over 9 zeros. Isn't it better if I just write 10 to the 9th?
Yeah.
Isn't that better?
Oh, yeah, so much better.
10 to the 9th instead. And instead of writing this, I should just write 10 to the 7th. Instead of writing this, I should write 10 to the 5th. And this one, I write 10 to the 3rd. And I think if I do it that way, I start to see, maybe I can write this as a formula. Yeah? Any questions on what I've done so far? Now, this stuff out here is not part of this pattern, right? I've got the 2 and the 10th. Those are like uniquely their own thing, right? So now I'm going to do this. This is equal to 2 plus a 10th, okay, plus, okay, what I see here is a pattern that my numerators are always 34s, right? And then my denominators are always powers of 10, starting with 3, and they're odd numbers, right? Odd power, odd power, odd power. So do you know how to generate the odds starting at 3? 2. We need the odds, not. I think you're starting at. You said n plus 2, right? That starts at 3, but then it would be 3, 4, 5, 6, 7, 8. We want the odds starting, right? Notice these are all odds, right? 3, 5, 7, 9. We want the odds starting at 3, which would be what? 2n plus 1. So remember I put the common formulas. I said we should learn these, we should understand these. This is why. So I'm realizing now that the rest of this can be rewritten as a sum, n equals 1 to infinity a 34 on top that never changes, and on the bottom 10 to the 2n plus 1, which would create 10 to the odd power starting at 3, and then it would just continue popping off the rest of those.
So is this the calculator you do?
What's that?
Is this the calculator you do when you punch in stuff like this? Or desk?
Oh, to convert, I actually don't know what algorithm a computer would use to switch. There's other algorithms other than this. In fact, my daughter had a problem like this the other day and had to do it without series. So it can be done mechanically by hand with no calculus.
That was like the one divide everything by 9 thing.
So your daughter.
You can, no, you just, like, you can multiply everything here. You multiply everything by 10 first, and that moves the decimal point over one place, and then you multiply by 100, and then you subtract, and then like all the remainder stuff cancels, and yeah, and it winds up, and there's different ways, there's different algorithms, so you might be talking about something different than the one I am.
Can constants be pulled out of the summation?
Yeah, constants can come out of sigmas, so you can pull a number by itself out. We actually are free to do that, or we can leave it in there and it can become part of the A. It's really our choice.
But it's portable. Like
It's portable. It can come
That
out.
whole thing.
Constants only, though. Constant. You can't
Same
bring
with
out.
the sigma as well. The sigma can just move around and be. But if you had a series of, or I'm sorry, if you had a collection of numbers and they all had sigmas involved, you could take them out and combine them. And
I think. I don't know. I'm not sure what you're. I'm not sure how you're meaning to combine them, but
yeah, I got you.
the only way you can add two series together is if they're convergent. So if you have two series and you want to add or subtract them, you're only allowed to do that if they're both convergent. You can't, because when you add them, something might happen, then you might think, oh, it converges, but if one of them diverged to begin with, then none of it's valid. So we have to be careful with arithmetic operations with series.
rules are the same as with the integral, right? All that stuff.
Basically, they're the same as the integral. Yeah, because it's just, the integral is like a limit of a summation, or a limit of a sigma, right? What did I say?
You said ligma.
Oh. All right. Okay, look, we need to get this to geometric, all right? Let's get this to geometric. So I think one way to see this, let me just focus our attention on this real quick. One way to see this, do y'all want me to pull the 34? I really don't care. Leave it? Okay, leave the 34, and then notice this. This is kind of not a huge like revelation, but is that the same thing?
Yes.
Why?
I don't think so, because the.
So what do you do when you have a fraction to a power? You apply the power to both the numerator and denominator, right? If I apply this to the 1, what's 1 to any power? 1, right? And then over 10 to that power. So that is actually the same as this. That's a vital thing to see here. Now, that's looking more geometric, right? This needs to look like what, though? And minus 1. It's 2n. How am I going to resolve the 2n? Here's how. Okay, so I'm going to do this. First, I'm doing this. Why? Because I can, right? That algebraically is okay. I can split this into two factors using the plus 1. I do 2n on this one. I do a 1 on this one. I'm not writing the 1. I'm assuming you understood that, right? That's the same. And that's great because I can just take that 1/10 and put it underneath the 34 out there, right? So I've got, I'm just working with this. Remember, I have a 2 plus 1/10 out in front. Okay, so I'm working just with that sum. I now have sum n equals 1 to infinity. 34 and that 10th comes, I'm not going to reduce it yet. I'll reduce it on the next step. 10 over 34. And now this is 1/10 to the 2n. Little better, right? A little better? Trying to get it to an n minus 1? All right, so now I'm going to use another property of exponents that's going to be useful to me. And I think I'll write it here on the side first, right? Just right here, I'm just going to write it. 1/10 squared to the n is the same as 1/10 to the 2n. In other words, if you have something to a power, you multiply the powers, don't you?
Yeah.
And so writing 1/10 to the 2n is the same as writing 1/10 squared, all of that to the n. But what's 1/10 squared?
1 over 100.
1 over 100.
Yeah.
So this is really 1 over 100 to the n. So I'm going to write 34 over 10 and then 1 over 100 to the n. Almost there. Minus 1 plus 1. Right? So next line, 34 over 10, sorry. Then 1 over 100 to the n, and then minus 1 plus 1. You don't have to show that step if you don't want to. You could just go to the next step, but I'm showing it here. So this is sum n equals 1 to 100, 1 to 100, 1 to infinity. All right, 34 over 10 times 1 over 100 to the n minus 1 times 1 over 100. Take that, move it over here. (34 over 1,000), 1 over 100 to the n minus 1. Geometric.
Oh, right.
We are doing geometric.
Well, I'm saying it's now the form that I can use the formula for, right? What's a for us? 34 of 1,000. I could reduce that. I'm not going to. 34 of 1,000 is a, right? And then r is 1 over 100. Is the absolute value of r less than 1? Yes, so this should converge. So what does this converge to? A over 1 minus 1 over 100. And that's 34 over 1,000 over 1 minus 100 is 99 over 100. And now you can flip it and do all that fun stuff. 100 over 99. And then you get some stuff to go away here, like 2 of these zeros can go away. And you get 34 over 990. Okay. That's not our answer. Remember, we still had in front of this what? 2 plus a tenth, right? This was just the series part. Right now, if someone on their calculator do 34 over 990, and you're going to get 0.03434. You're missing the 2 and the 1/10. So we still need to put that in there. So now we go back to where we were. We had 2, so this is like 2 plus a tenth, plus we had the sum, right? The sum was here, but now that sum became that fraction. Like that. We have this, right? We need a common denominator between all of these, and then we put them together and we will have a final fraction. So 2 over 1 plus 1 over 10 plus 34 over 990. I'll need some help here. Okay, I have to get a 990 down here, I have to multiply top and bottom by 990. 990 times 2, that's 1,000, 2,000, 18. Well, hold on, don't reduce. I don't want reduced. I just want the full. What is it?
1,980.
1980 over 990 right here. Plus, now you have to multiply top and bottom here by what? 99. So 99 over 990. And then plus 34 over 990. Add across the top. 279.
2113.
2113, is it 13? Or I was thinking 2113?
Yep.
2113 over 990. Now that fraction might reduce, and I don't care if it does. Plug that into your calculator and see if you get 2.1343434. Yes? Right, that is it. Okay, that's more, I mean, that's not really like a like a nice application of this. It just shows you that you can take any repeating decimal and find the fraction using geometric series. All right, moving on. Your next series. We have to harmonize here. So the harmonic series is, I think, the easiest series out of all series that we're going to see, because all harmonic series do the same thing. They all diverge, all right? So let me give you the example, and I'm going to do just a general argument proof. This is not going to be a rigorous proof, but I think I can convince you. So harmonic, okay, I'm talking about harmonic here. Your first example of a harmonic is this series here. So why is this not geometric? Missing the a. So with geometric, you have to have a number raised to a power, and that power has, the n is up in the exponent, isn't it? The n here is up in the exponent. Here, the n is just the denominator, right? It's not in the power of something. And so this already cannot be written as geometric. So what is the series? Let's just start plugging numbers in. This is 1 over 1, 1 plus a half plus a third plus a fourth plus a fifth. You get the idea, right? But to prove it to you, I'm actually going to write a lot of these out. And like I said, this is a very loose proof. This is not a rigorous proof. Okay, I'll go out to 16. 1 over 16. That's what this is, right? Let's check. Let's do the very first test we learned, the n-term test. So the n-term test says you ignore this, you look at that, you take the limit as n goes to infinity. What happens when n goes to infinity to that? It goes to 0, which tells you? Careful. The n-term test, if that goes to 0, it tells you nothing. This is that failed pregnancy test that none of the lines show up, right? That's what we were talking about? It's like, oh shit, you need a different test, right? That's what this going to 0 tells you, nothing. All right? So we don't know what happens. So we need something else. Okay, well, it's not geometric because we don't see, like, do y'all see that you don't see things to a power? Okay. All right, so what happens to this? My proof of this is going to be this. Yeah, all right. So do you all agree that if I put these two together, just those two,